We are going to look at the two common methods we use for leveling: trigonometric leveling and differential leveling. In differential leveling, there are two common calculation methods. The first one is rise and fall method, and the other one is height of instrument method. We are going to see the examples of those two calculation methods. What is leveling? Leveling is the method or process we use to determine the elevations of the points on the Earth's surface. So why do we need the leveling? Leveling is important to produce maps and plans showing the contours. It means the elevations of the topography. We need leveling to design roads, railways, and other building structures to be suitable to the existing topography. To set our construction projects in accordance to its design. To calculate volumes of the earthworks. To monitor the subsidence or elevations of the ground surface. Two common methods we use in leveling include differential leveling and trigonometric leveling. Firstly, let's have a look at the trigonometric leveling method. It is used for the short lines up to about 305 meters just to avoid the large area of the curvature of the Earth. From its name, this method uses the math formulas for a right triangle to determine the elevation. So we set up the instrument at point A, and we have a prism or reflector at point B, and we want to measure the elevation difference between A and B on this slope surface. You can use a steel tape to measure the height of the instrument from point A to the telescope level, HI. And you also know the height of the rod from point B to the slope line over here, from B to D. So from the relationship of a right triangle, we can easily determine the vertical distance from the telescope level to point D. So now V can be easily determined from one of the formulas here, either from the slope distance and the vertical angles Z or alpha. These angles are known as well from the readings from the instrument. So once we know the vertical distance V, so now we can easily determine the elevation from A to B. So now let's look carefully. From A to B is actually the distance from A to the telescope level first, HI. And then we add up the vertical distance from telescope level to point D, which is V, already calculated from previous step. So you add V. So it means the vertical distance from A, this level, all the way to D. And now you minus the height of the rod, R. So from D you minus the rod reading R. So you minus this distance. So you go down to B, and that's going to give you the change in height or elevation difference between A and B vertically. So that is what we want to calculate. That is the elevations difference between A and B. Now we have an example for the trigonometric leveling. To determine the height difference between point A and point B on a steep slope, we have to use the trigonometric leveling method. So in this diagram, we set up the instrument at point A. We can measure the height of the instrument HI, and we point the telescope to the rod at point B. You can then determine the height of the rod from B to D. That's the value R. The vertical angles can be determined from the instrument Z. So now, from the formulas in the previous slide, you can determine the vertical distance from the telescope level and point D. So now we can carry on with determining the elevations difference between A and B by adding the vertical distance to the height of instruments and then minus the rod reading. In this case, they mentioned that the height of the instrument equals the rod reading. So then this part is 0. And if you know the elevation or reduced level of point A, so then you can easily determine the elevation or reduced level of point B. Elevation of point B equals elevation of point A plus the difference in height between 2 points. So that's the procedure. You just need to replace the figures we have from this example. The next method we use is differential leveling. The key thing is that we use a level. That's why you are going to have a horizontal line of sight through the telescope of the level. From point A to this horizontal line, you will have the backside reading. Backside reading is the first reading once you set up the instrument. Then you rotate the telescope to take the foresight reading at point B. The foresight reading then is used to determine the height difference between A and B. So height difference between A and B is this much. And this length equals backside minus foresight. So backside minus foresight, that gives you the height difference between A and B. So that is the principles of differential leveling method. Some terms and definitions in differential leveling. Reduced level. That's the elevation or the vertical distance from a datum to a point or object. We are going to use the term reduced level quite a lot. Benchmark. We will need to use the benchmark, a point of non-reduced level, to calculate the reduced levels of points of unknown elevations. backside in the diagram before, that is the first reading in the leveling after setting up the instrument. The foresight, the final reading at a setup. Leveling datum, a reference surface, normally the mean sea level. It is used as the origin, the level 0, to calculate the reduced levels of the other points. To determine the reduced levels of point X, which is unknown, from the benchmark A, which is known, there are two calculation methods. The first method is called the rise and fall method. Once you set up the instrument somewhere in between point A and point X, you take the first reading, which is the backside reading, and then you take the second reading, turn the telescope, take the second reading at point X. You have the foresight reading. So this is the backside reading and this is the foresight reading. The first step is to calculate the height difference between benchmark A and point X. So the height difference equals backside minus foresight. So this is the height difference in the diagram. If the result is positive, so we say there's a rise from A to X. The elevation increases. If the result is negative, then you're going down. So that's a fall. The rise means a positive height difference. The fall means the negative height difference. So that's why they call the rise and fall method. Reduced level of point X then equals reduced level of point A plus the rise or fall. So that's the formula. In this example, we have the height difference of 0.216. That is a rise from A to X. Reduced levels of point X equals reduced level of point A, which is known, 26.125. Then you add the rise to the benchmark reduced level. You get reduced level of point X, 26.341. Now, let's have a look at this situation where you have the point G measure above the height of the instrument, point A in this case. We're going to turn the stuff upside down. So 0 is going to be here and down here. If you take the reading, the distance from A to the line of sight, 3.456 meter. But in this case, we have to put negative sign before the reading. For every point, if they are above the line of sight. So the reading is now minus 3.456 meter. The calculation is still the same as the previous steps. That is the subtraction of the readings. So, for example, if you set up the instrument and you take the first reading towards point B and you get 2.248, then you go to point A, you take another reading and it's now minus 3.456. The height difference is the subtraction of these two readings. So 2.248 minus 3.456, that gives you a height difference of 5.704 meter. So actually you have the distance here 2.248, and towards this point above you need to add this distance. So that's why if we have minus here, we have to minus again over here to get the true height difference between A and B. Remember that you put a minus for all of the points above the line of sight. We call the inverted staff reading. The calculation is still the same if you use rise and fall method or height of collimation method. The only thing is that you need to put minus before the reading for the inverted staff. Now, let's look at another method to calculate the reduced level of point X from the benchmark A. The name of this method is height of plane of collimation. This is the height of the collimation line. It's also called the height of instrument method. This is the height from the datum to the telescope level. So now you know the backside and the foresight, and we calculate the elevation between A and X. We will start from elevation of benchmark A. So from the datum to point A. And now we add the backside. You will get the reduced level of the line of sight, or the instrument, or the plane of collimation. So they're all the same. So you get to this level. So the first step, the height of instrument equals known points elevation plus backside. Height of instrument equals elevation at benchmark A plus backside. And from this level, now you minus the foresight. So you are going to get the reduced level of point X directly without knowing rise or fall between A and X. Reduced level of point X equals height of collimation minus the foresight. New point equals height of collimation or height of instrument minus foresight. So this level minus the foresight, you get the reduced level of point X. So this is the result. 26.341, which is higher than 26.125. So now you know that point X is higher than benchmark number A, benchmark A. Next, we have an example to calculate the reduced level of point B, which is unknown, from point A, which is known as it is a benchmark. You can use the rise and fall method, and then you can compare to the height of instrument method. If you use rise and fall method, the first step is calculate the rise or fall. Backside minus foresight. So that gives you a positive value. That is a rise. Reduced level of unknown point equals reduced level of point which is known plus the rise or fall. So now let's use the height of instrument method and compare to the rise and fall method. You should have the same results for the reduced level of point B. So then, what do you need for differential leveling? You will need a tripod to attach the level onto it. You will need a staff so you can take the readings to know the length from the points you're measuring and the line of sight. And the most important is the level. There are several types of level. It can be a dumpy level, a simple level which has a fixed line of sight, and it has the foot screws over here, the focus knob, refine adjustment, and the eye pits. Another type of level is the automatic level. It's very similar to the dumpy level, except that it has the automatic compensator. What does it mean? It means if your level is not completely horizontal, then the compensator here will adjust the line of sight and it will make it horizontal, so give you the accurate results compared to the dumpy level. So you see that if your telescope is not completely horizontal, then the line of sight is still adjusted due to the automatic compensator to make a horizontal line here and give you the accurate result. So now, before you can take the reading, you need to know how to set up a level. So you will need to attach the level onto a tripod and make sure that this tripod is stable on the ground. We use the 3 foot screws at the base of the level to adjust its level. So what we do is using a left thumb rule. In the next slide, we're going to explain that. So here, we will use the left thumb rule to adjust the base of the level. And we have the bubbles over here. So when the bubble is in the center of the circle, it means your levels here is now in the horizontal surface, or horizontal plane. So it's ready to take the reading. To make this work, firstly you need to adjust only 2 screws first and look at the bubble. Normally it's not in the center at first when you attach the level to the tripod. So you need to turn the 2 foot screws only either towards each other or away from each other. In any direction you can turn the 2 foot screws. But if you turn the 2 foot screws here and your left thumb is moving to the right, then the bubble is moving to the right as well. If your left thumb is moving to the left, then the bubble is moving to the left as well. So that's why we call the left thumb rule. Remember that. So when the bubble here is out of the center, you bring it to the center using the left thumb rule, turning the 2 foot screws first. Once you have the bubble at the center line, of the 2 full screw you've done in the first step. So now you turn the last full screw here, also using your left thumb. So then if you need to bring it down, you're going to move your left thumb anti-clockwise this way. So you can bring it down. This is your left thumb move, and then the bubble move the same way. You also need to use steps with the graduation here to give you the indication of the length from the point you're measuring and the line of sight. So you need to hold the stuff vertically. So that's the key thing. And you may need to use the bubble to attach to the stuff to check whether it's vertical or not. A change plate. When the distance is too far, for example from benchmark A to station C, so you can't use only one setup. So you need to have one more setup over here. So you will need some points in between A and C. So when the ground is not stable, you will use a change plate to put somewhere in between A and C. And we use that as a turning point or a change point to connect A and C. So setup number 1, you measure the height difference between A and the turn point over here. And setup number 2, you measure the height difference between this change point and station C. So you can finally calculate the height difference between A and C later on. So that is the purpose of using a change plate at a change point or the turning point. Staff reading. It's important to know how to take a correct reading through the telescope. So remember, always use the center crosshair for the elevations. Never use the stadia hair at the upper part or the stadia hair at the bottom part. Those are for distance measurement, not for leveling. So use the center crosshair through the telescope. That's the correct line to take the reading. So the graduation on the staff, you're going to see the numbers over here. So numbers here are the hundredths of millimeters. So 13, it means 1300 millimeter, or 1.3 meter. You're going to see the line under those numbers. So that's where we have the hundredths of millimeters. 14 millimeters, 1400 millimeters for the next line over here, or 1.400 meter. So each of the red block or the blank block over here equals 10 millimeter. So that's why for this reading, so you can see that it equals 1400 at this black line over here, and you add 10 mil, 20 mil to that figure. So then the reading over here is going to be 1400 plus 20 mil. So you have 1420 mil or 1.420 meter. So that's the example. So now you have other examples of staff reading. So those numbers here are hundreds of millimeters, and you will add 10 meters for one solid block or a blank block over here. If our line, telescope line, is somewhere in the middle of a solid block or somewhere in the middle of a blank block like this, so you need to do your own adjustment and to see how many millimeters you're going to add from the nearest numbers from the staff. For example, so here you can see that at the bottom of letter E, so you have a line here, and that is 30, 100 or 3 meter. So if your center crosshair is somewhere in between the first block here, so one full block here is 10 mil, so you add 5 mil to that level, so you're gonna get 3,005 millimeter or 3.005 meter. So what about this point? So we have 30, 100 from here. So you add 30, 10, 30, 20, 30, 40, 30, 30, 30, 30, 30, 40, 30, 50. And now you have about 3 or 4 mil more. So it's going to be 30 and 1, 2, 3, 4, 5, 30, 50, and another, let's say 4 mil in this case. So you're going to have 3.054 meter. So that's how you take the reading, and you have to do your own judgment to know the level of the staff, and then you will take the reading and take note and calculate the results later on. For more instructions about leveling, you can watch the videos from the links below.